In this video, we are going to talk about hyperbolic functions. Hyperbolic functions normally arise as a result of solutions to differential equations and Laplace equations. Now, remember the equation of a circle. Remember that we said that equation of a unit circle is x squared plus y squared equals 1. Now, and then in trigonometry, we said that x is equal to cos theta, and then y is equal to sine theta. So if we insert x and y into this equation, it becomes cos squared theta plus sine squared theta equals 1. So this is the equation that we get in trigonometry. But then hyperbolic functions are normally functions that come in the form x squared minus y squared equals 1. So this is the equation for a unit hyperbolic function. Now, instead of saying cos theta, here we say x is equal to hyperbolic cos theta. So in this is known as the cos function, and then y is equal to the hyperbolic sine theta, and that is the sinh function. So now if we insert these two into the equation, it becomes cos squared theta then minus sinh squared theta equals 1. So this is the equation for the unit hyperbolic function. Now, the trigonometric functions are normally given in terms of the adjacent, hypotenuse, and then opposite. But then hyperbolic functions are usually given as a sum of both odd and then even functions. So now, by definition, the hyperbolic cosine function is given as half, then into brackets exponent x, then plus exponent minus x. Then the hyperbolic sine function, so hyperbolic sine theta, is given as half into bracket exponent x minus exponent minus x. So having gotten these two, then we can find the hyperbolic tan function. So the hyperbolic tan function, tan theta, is given as, now that is, we know that from trigonometry, tan is sine theta over cos theta. So for the hyperbolic tan function, that is also given as hyperbolic sine theta then divided by hyperbolic cos theta. So we are going to get the hyperbolic sine theta divided by hyperbolic cos theta, and this is given as half of, we said the sine is exponent x minus exponent minus x, then divided by half into bracket exponent x, then plus exponent minus x. So if we do this division, then we are going to get the hyperbolic tan function given as exponent x, then minus exponent minus x divided by exponent x and plus exponent minus x. We have already established that hyperbolic cos x minus hyperbolic sine x, cos squared x minus hyperbolic sine squared x is equal to 1. And then we said that by definition, the hyperbolic cosine function is given as half, then into bracket exponent x plus exponent minus x. Then the hyperbolic sine function is given as half, then exponent x minus exponent minus x. So now let's use this to prove this hyperbolic identity. So now let's insert it into this equation. So if we insert it into this equation, we will get into bracket half then times exponent x then plus exponent minus x, then bracket close, all squared, then minus into brackets half, then exponent x, then minus exponent minus x, bracket close, all squared. So now 1 over 2 squared is the same as 1 over 4. And then times, if we square exponent x, we are going to get exponent 2x. Then plus, if we square exponent minus x, we are going to get exponent minus 2x. And then now we are left with another term, that is 2 times exponent x times exponent minus x. But remember that exponent x times exponent minus x is equal to exponent x minus x, which is equal to exponent 0, and exponent 0 is 1, so this is equal to 1, and therefore I will just write plus 2 times 1, and that will become plus 2. So now all of this, then we subtract it from minus, then we repeat the same thing here, so this becomes minus 1 over 4 times exponent 2x, then in this case it becomes plus exponent minus 2x, then here instead of plus 2, here becomes minus 2. Now we can factorize 1 over 4 out of the equation, so this is equal to 1 over 4, we factorize that out. So here's exponent 2x, then here's exponent 2x. So now if we factorize that, we are left with exponent 2x minus exponent 2x, and then so here will become exponent 2x, then minus exponent 2x, then here becomes exponent minus 2x minus exponent minus 2x, so here becomes plus exponent minus 2x, then minus exponent minus 2x, then here becomes plus 2 minus minus 2, and that becomes plus 2 plus 2, then the big bracket close. So this is equal to 1 over 4, and then we open the bracket, exponent 2x minus exponent 2x is 0, then plus exponent minus 2x minus exponent minus 2x is also 0, then plus 2 is 4. So this becomes 1 over 4, then times 4, and this is equal to 1. So you can see that we have been able to prove that hyperbolic identity, that cos squared x minus sinh squared x is equal to 1. Now, having gotten this, can we derive other hyperbolic identities from this equation? Now, cos squared x minus sinh squared x is equal to 1. So let's divide through by cos squared x. So we divide here by cos squared x, divide here too by cos squared x, and we divide here too by cos squared x. So this cos squared x and cos squared x will cancel, so we left with 1 minus. Now remember that we've said that sinh squared x divided by cos squared x is the hyperbolic tan, so 1 minus the hyperbolic tan squared x, and then this is equal to 1 over cos squared x is the same as the sec hyperbolic sec function, so sec squared x. So this is also another hyperbolic identity. Now let's prove the last one, and then with the last one, so let me repeat this identity, cos squared x minus sinh squared x is equal to 1. So instead of dividing through by cos squared x, we are going to divide through by sinh squared x. So this becomes divided by sinh squared x, then here too is divided by sinh squared x, and here divided by sinh squared x. So at the end of the day, this and this will cancel out, just as this one and this cancelled out. So Now cos squared x divided by sinh squared x is the same as 1 over the hyperbolic tan, and that will give us the cot. So it will give us the hyperbolic cot. So this becomes cot squared x then minus 1 equals, now 1 divided by sinh squared x is the same as the cosec, hyperbolic cosec squared x. So now you can see that we'll be able to prove 3 very important hyperbolic identities. The first one being cos squared x minus sinh squared x equals 1, and the second one being 1 minus tan hyperbolic tan squared x is equal to the hyperbolic sec squared x, and then the last one is the hyperbolic cotangent, which is the hyperbolic cot squared x then minus 1 equals the hyperbolic cosec squared x. So these are, in terms of hyperbolic functions, these are the hyperbolic identities. At this point, let's talk about the Osborns rule. The Osborns rule is used to convert trigonometric functions to hyperbolic function. So what the Osborns rule says is that if you want to convert a cosine function, so like let's say cosine x, you can convert it to a hyperbolic function by replacing cosine x with the hyperbolic cos function x. So you can replace cosine x with cos x, and then with the sine x, you replace sine x with I, then the sinh function or the hyperbolic sine function, so I sinh x, and then with tan x, you replace tan x with I, then hyperbolic tan x. Now this I is defined as I squared equals minus 1. It is the same I that is encountered in complex numbers. In the truest definition of the Osborns rule, it says that replace cos function with cos function, then sine function with sinh function. And then if you have any product or implied product of 2 sine functions, then you replace it by the minus the product of the 2 sinh functions. So what it means is that, for example, if you have sine A then sine B, then sine A sine B is replaced by, this is the same as minus sinh A then sinh B. That also we have tan squared A now can be written as sine A divided by cos A. So because this is a product of 2 functions, then in terms of the hyperbolic tangent function, tan squared A becomes tan hyperbolic tan squared A equals, now this becomes minus sinh A divided by cos A, because we have a product of 2 sine functions. Now let's write the trigonometric identities. We know that from trigonometry, cos squared theta plus sine squared theta is equal to 1. And then we also know that 1 plus tan squared theta is equal to sec squared theta. And then we also know that 1 plus cot squared theta is equal to cosec squared theta. So now we want to convert these 3 trigonometric functions into hyperbolic functions using Osborns rule. So now you replace cos x with cos x. So if it is cos squared theta, then cos squared theta becomes cos squared theta. But if you have a product of the sine functions, you replace them by the negative of the product of the hyperbolic sine function. So here sine squared theta, it becomes minus sinh squared theta, and that is equal to 1. Now let's come to the second one. Here's 1 plus, so 1. Now you can see that there is an implied sine function here, because tan squared theta is the same as sine theta times sine theta divided by cos theta times cos theta. So here becomes minus the hyperbolic tan squared theta equals sec squared theta. So it becomes the hyperbolic sec squared theta. So we've written that identity too. Now let's come to the last one, which is this. So this is 1 plus. Now this is cot is the same as 1 over tan. So but we know that there is an implied product of sine functions in the tan function. So since here is cot, then it becomes 1 minus the hyperbolic cot squared theta. Then we also have a product of two sine functions here, equals minus cosec, hyperbolic cosec squared theta. So rearranging them, if we multiply through by 1, then we will see that it becomes cot hyperbolic cot squared theta, then minus 1 equals the cosec squared theta. And what I mean is the hyperbolic cosec squared theta. So we see that using the Osborns rule, we've been able to convert all the trigonometric identities into their corresponding hyperbolic identities. So let's prove why the Osborns rule work. The Osborns rule work because let's first state the hyperbolic cosine function. We defined it as half exponent x, then plus exponent minus x. And we define the hyperbolic sine function as half exponent x, then minus exponent minus x. So having given these definitions, let's remember Euler's law. What does Euler's law state? Euler's law states that exponent I theta equals cos theta, then plus I sine theta. And then also exponent minus I theta equals cos theta, then minus I sine theta. So now if we have hyperbolic cosine I theta, what will we get? Using this definition, then that is equal to half, then bracket open, exponent I theta, then plus exponent minus I theta. But we said that from Euler's law, exponent I theta is the same as cos theta plus I sine theta. So this is equal to half, then exponent I theta is the same as cos theta plus I sine theta, and then plus exponent minus I theta is cos theta minus I sine theta, bracket close. So this is equal to half. Now cos theta plus cos theta becomes 2 cos theta, and then plus half, then I sine theta minus I sine theta is 0. So this becomes half of 2 cos theta, and that is equal to cos theta. So you see that starting from cos I theta, then we move from cos I theta to cos theta. In other words, cos I theta is equal to cos theta. Now, instead of doing cos I theta, let's replace theta with another I theta. So this becomes cos. Now, there's already I. We are replacing times I theta, and that is equal to cos theta. So this becomes cos, then theta is now I theta, so cos I theta. Now I times I is I squared, but remember that we've already said I squared is equal to -1 from complex numbers. So this becomes cos into bracket I squared theta equals cos I theta. So now, then this is equal to cos minus theta equals cos I theta. Now, the cos function is an even function. If we say an even a function is an even function, what does it mean? It means that if you find f of minus x, it is equal to f of x. And then if a function is odd, then f of minus x is equal to minus f of x. So this is an odd function and this is an even function. So because the hyperbolic cos function is an even function, then cos minus theta can be written as cos theta, and that is equal to cos I theta. So now we were able to show that cos I theta is equal to cos theta, and we have also been able to show that cos theta is equal to cos I theta. In other words, both the theta and then the I theta are interchangeable. So because they are interchangeable, then we can confidently conclude that cos theta is equal to cos theta. Let's do the same thing with the hyperbolic sine function. We say that the hyperbolic sine function is giving us half into bracket exponent x then minus exponent minus x. So let's solve change I theta. That is equal to half of into bracket exponent I theta then minus exponent minus I theta. But remember Euler's law. So this can be written as equal to, so this is equal to half then into bracket exponent I theta according to Euler's law is cos theta and then plus I sine theta, and then it's minus into bracket cos theta minus I sine theta. So this is equal to half. Now cos theta minus cos theta is 0, so we are left with I sine theta, then minus I sine theta becomes plus I sine theta. So this is equal to half of 2I sine theta, and half of 2I sine theta is the same as I sine theta, and that is exactly what the Osborns rule says, that hyperbolic sine, let's say x, is equal to I sine x. From trigonometric functions, we said that sine a plus b is giving us sine a cos b, then plus sine b cos A. So now let's use Osborns rule to convert this into hyperbolic sine function. So in terms of hyperbolic sine function, so hyperbolic sine A plus B is equal to, remember we said cos x, replace it with cos x, and then the sine x, as we have already proved it, you replace it with I sin x. But I sin x is also from our previous proof, can also be replaced by sin x. The only time this changes is when you have a product of two sine functions, then you change the sign to a minus. So hyperbolic sin A plus B becomes hyperbolic sine A, then hyperbolic cos B, and then now plus hyperbolic sine B and hyperbolic cos A. Now let's write sine. So what then is sine A minus B? From trigonometry, it is sine A cos B minus cos A sine B. So just as we did here, let's write the hyperbolic expansion of sine A minus B, and that becomes hyperbolic sine A, and then hyperbolic cos B. Now, since they are not product of the sine functions, then it becomes minus and hyperbolic sine B. Then it becomes hyperbolic sine into bracket A plus B equals hyperbolic sine A, then hyperbolic cos B, and then plus hyperbolic cos A, then hyperbolic sine B. Now let us add this. Let's assume this is equation 1 and this is equation 2. If we add equation 1 and 2, you see that this part will go to 0, and this becomes 2 sin A cos B equals, now sin into bracket A plus B, then plus sin into bracket A minus B. So now if we divide through by 2, then sin A cos B equals half of into bracket sin into bracket A plus B, then plus sin into bracket A minus B. This is very, very, very important equation when we come to techniques of integration. Another thing is that we could have also subtracted equation 1 from equation 2, and if we do that subtraction, this part goes to 0, so this becomes 2 cos A sin B, and then that is equal to into bracket, that is equal to sin A plus B, then minus sin A minus B. So if we make cos A sin B the subject, cos A sin B the subject, this is equal to half of into bracket sin into bracket A plus B, then minus sin into bracket A minus B, bracket close. Having understood the sinh functions clearly, let's come to the cos functions. We said that from trigonometry, cos A plus B is equal to cos A cos B, then minus sine A sine B. So in terms of hyperbolic functions, then cos A plus B is equal to cos A becomes cos A, then cos B becomes cos B. But remember, the product of two sine functions, so we need to change the sign to plus, and that becomes sinh A using Osborns rule. Sinh A, then sinh B. Now let's write cos into bracket A minus B, and that becomes, from trigonometry, this is cos A cos B, then plus sine A sine B. But in terms of hyperbolic functions, cos A minus B equals cos A cos B. Then now product of two trigonometric functions, product of two sine functions, so it becomes, we need to change the sign, so this becomes minus sinh A, then sinh B. So let me write this equation beneath this. So cos A plus B equals cos A cos B, then plus sinh A, then sinh B. So now let's assume this is equation 1 and equation 2. If we add equation 1 and equation 2, this side of the equation goes to 0. So we will get 2 cos A cos B equals cos to bracket A plus B, then plus cos into bracket A minus B. So if we make cos A cos B the subject, then we are going to get that to be equal to half of cos into brackets, here's cos A plus B, then plus cos into bracket A minus B. And then we could have also subtracted. So if we subtract equation 1 from equation 2, this side goes to 0, and here becomes 2 sinh A sinh B equals cos A plus B, then minus cos A minus B. So making sinh A sinh B the subject, and that is equal to half of into brackets cos A plus B, then minus cos to bracket A minus B, bracket close. So now let me just rewrite the hyperbolic expansion of cos A cos B and explain something. So cos A cos B is equal to half of into bracket cos to bracket A plus B, and then plus cos into bracket A minus B, bracket close. Now let's write sinh A cos B, and this is equal to half of into bracket sinh a plus b, then plus sinh into bracket a minus b, bracket close. Now what we want to do is to say let x to be equal to a plus b, and then we let y to be equal to a minus b. Now let's say this is equation 1 and this is equation 2. If we add equation 1 and equation 2, b goes to 0, so we'll get 2a equals x plus y, and therefore a is equal to x plus y over 2. And then now if we subtract equation 2 from equation 1, so 2 minus 1, we are going to get x minus y equals, the a goes to 0, 2b, so b is equal to x minus y over 2. So what we are going to do is that we are going to replace here a with x plus y over 2, and then b with x minus y over 2. So what it means is that now let's multiply through by 2, so this half will go away, so this becomes 2, and then change. Now a becomes x plus y over 2, x plus y over 2, then cos b is x minus y over 2, and that is equal to, now sinh a plus b is x, so this becomes sinh x, and then sorry, here is sinh, and then sinh a minus b becomes sinh y, so plus sinh y. So this is also a very important equation as far as integrations are concerned. And then the last one, we could use the same principle to write for this equation. So cos a becomes cos into brackets x plus y over 2, and then cos b becomes cos into bracket x minus y over 2, and then that is equal to cos a plus b becomes cos x, and then plus cos a minus b is cos y. So you can see that sinh x plus sinh y is equal to 2 sinh x plus y over 2 cos x minus y over 2, and then cos x plus cos y equals cos x plus y over 2 cos x minus y over 2. Very, very, very important equations. So we can use this same idea to write the various hyperbolic identities for the other hyperbolic expansions of a plus b. Now we said that cos a plus b is equal to cos a cos b, and then plus sinh a, sorry, let me put this into brackets, then sinh b. So now let's use the definition of the cos and then the sinh functions to prove this identity. We said that cos x equals half exponent x, then plus exponent minus x, and then sinh x equals half, and then into brackets exponent x minus exponent minus x. So cos a plus b can be written as half into bracket exponent in one bracket a plus b, and then plus exponent minus into bracket a plus b. So we are just using this definition to expand this. So this is equal to half exponent A exponent B, then plus exponent minus A exponent minus B, bracket close. Exponent theta equals cos theta plus sinh theta, and then exponent minus theta is equal to cos theta minus sinh theta, and therefore this becomes equal to, using this idea, and then we want to use that to expand this, so that becomes half into bracket exponent A becomes into one bracket cos A plus sinh A, and times exponent B cos B plus sinh B, and then plus exponent minus A into bracket cos A. Remember, we are using this identity to expand. Then minus sinh A, then times exponent minus B cos A cos B minus sinh B, bracket close. So now let's expand this. So this is half. Now cos A times cos B becomes cos A cos B, and then plus cos A times sinh B cos A sinh B, and here becomes plus sinh A cos B, then plus sinh A sinh B. So we are done with the expansion here. So with this, cos A times cos B becomes plus cos A cos B, and then minus cos A sinh B. Then for the last one, sinh A times sinh B, I'm going to write that as plus sinh A sinh B. Now there is a missing term here, which is minus sinh A times cos B, so it becomes minus sinh A cos B. So you can see that there is sinh A cos B, sinh A cos B, so that these two can cancel. Then here is minus cos A sinh B, here is also plus cos A sinh B, so these two can also cancel. So at the end of the day, we are left with, so there is a bracket here, half into bracket. Now cos A cos B, then here is cos A cos B plus, so it becomes 2 cos A cos B. Then from there we have here sinh A sinh B plus sinh A sinh B becomes plus 2 sinh A sinh B, bracket close. Now if we divide through by 2, then these 2's will go away, so this is equal to cos A cos B and plus sinh A sinh B, and that is the identity that we started with, or a proven identity in hyperbolic functions. So now we could also use this same definition of the cos and then the sinh, the cos function and the sin function to evaluate sinh A plus B, and we know that sinh A plus B is the same as sinh A cos B then plus sinh B cos A. So let me write it here. So this is equal to sinh A cos B and plus sinh B and cos A. So we can also use what we have done so far to prove this, and we realize that that is also true.